Every intelligent machine begins with data. Before computers could recognize faces, understand language, or drive cars, they first learned something much simpler: how to find patterns. The first major step in that journey is called linear regression. Imagine we want to predict a student's exam score based only on the number of hours they studied. We already know the results for several students. Can a computer learn the relationship and predict future scores? Each row in the table represents one observation. The input feature is the number of hours studied, and the output is the exam score. In machine learning we call the input X, and the output Y. 6 students give us 6 XY pairs. Together, these observations become the training data. When we plot every observation, we notice something important. As study time increases, exam scores also tend to increase. Moving from 3 hours to 4 raises the score from 60 to 70, roughly 10 points for every extra hour. This relationship is called a positive linear trend. The computer tries many different lines. Some fit the data poorly, while others fit much better. The goal is to discover the line that minimizes the prediction error. This search for the best parameters is called fitting the model. Every prediction contains some error. Linear regression measures the distance between actual values and predicted values. These distances are called residuals. For example, the student who studied 6 hours scored 88, but this line predicts only 81. The gap of 7 points is that student's residual. The best model makes the total residual error as small as possible. In practice, each residual is squared before adding them up, which is why this classic method is called least squares. The algorithm learns by continuously adjusting two values: the slope, which controls how steep the line is, and the intercept, which determines where the line begins. With each adjustment, the prediction becomes more accurate. Here the best slope is about 9.3. Each extra hour of study adds roughly 9 points to the predicted score. And the intercept, about 32, is the predicted score with no studying at all. Now the model encounters a new student it has never seen before. Based on everything it has learned, it predicts the student's exam score. Slope times 7 hours, plus the intercept, 9.34 times 7, plus 32.1, is about 97.5. This ability to estimate unseen values is the essence of supervised machine learning. Of course, the line captures the average tendency. Real students will vary around it. A prediction is an estimate, not a guarantee. Let's recap. A straight line can summarize a trend. Residuals measure how wrong each prediction is. Learning means adjusting the slope and the intercept to shrink that error. And once fitted, the line can predict values it has never seen. Linear regression may seem simple, but it is one of the most important algorithms in all of data science. It powers forecasting, finance, healthcare, engineering, and countless real-world applications. In the next episode, we'll expand beyond a single input and discover how multiple linear regression combines many features to make even better predictions.